Alright, let's construct some representations using what we know. So, let's say we have representations rho 1 and rho 2 of G on vector spaces v1 and v2. Well, yeah, that's how it works. They're representations of G on v1 and v2. So we know what the direct sum of maps is. We can just put that here, and then the way we define this representation rho sub plus, I'll call it rho plus, is that you just take the direct sum of these two maps for any G and G. And then this works because you just check it. Well, if you take rho plus G composed with rho plus H, evaluate at some v1, v2, where v1 is in v1 and v2 is in v2, then you evaluate this, and that's going to give you rho plus G evaluated at this thing, and then you just do it again. And then because rho 1 and rho 2 are representations, you can combine these each into one, and then you get this. And then by definition, this is just rho plus of the product G times H evaluated at v1, v2. You do also have to check that this thing is in GL v1 plus v2, but it works. You can check that if you want. Or I think we can just appeal to the definition of direct sum of linear maps. That should work too. Okay, so this is how we define a representation on the direct sum. We can do the same thing. No, not direct sum. Yeah, direct sum. You can do the same thing on the tensor product. And it's pretty much identical, except you just take all of these direct sums and rotate them 45 degrees so that they become tensor products. So of course, like, you have to replace like, instead of considering this as an ordered pair, I wrote it as like this tensor product, but it's the same thing. It's the same argument, and you do it. Okay. We also have a representation V star, and so we have a representation of G on V star by, okay, so rho star needs to map to the general GLV star, so it needs to be a linear bijection between elements of V star and elements of V star. And V star itself consists of maps from V into C. So there's a lot going on here. And so if you want to figure out what rho star of G does, rho star of G is a map from V star into V star. And so to figure out what this is, we have to figure out what it does for each xi in V star. So rho star of G of xi is going to be a map from V into C. So in order to figure out what this is, we have to evaluate this at V. And so this will give us some complex number. And the way we do it is we just evaluate xi at rho sub G inverse V. And this is for all these things in here. So trust me on this one. I went through and I tried to write this out, and it gets really messy. And every time I would go to record this video, I would notice like another thing where it's not like the way that I had written it out was not completely intuitive, and it didn't make either there was an error or it was written in a way that didn't really do a good job of conveying what was going on. And that's sort of tough with something like this where you've got so many things going on. It's difficult to write these things with this much detail. So instead of like getting stuck here and trying to spend more and more hours trying to make sure that I have the best way to present this possible, I'm just going to tell you to do it if you want to figure it out. So you should check that and check that this works. And I'm also going to check it myself, but I'm not going to go through the extra steps of proving this the best way possible and then writing it down and understanding it to the point where I can actually present it really quickly. So I think the best thing is to just trust me so that we can move on to more stuff. So similarly, well, not similarly, but instead of V star, instead of considering maps from V into C, you could consider maps from a different vector space, say V1, into another vector space, say V2. So the collection of linear maps from V1 to V2, we can define a representation of G on this vector space by this thing. Okay, so again, we have to take this representation, evaluate at G, evaluate that at some map F from V1 into V2, and evaluate this at some element V1. And so what this is going to give us is it's going to give us row 2 of G. So row 2 is a representation on W. So row 2 will take in an element of W and spit out an element of W. So this thing that we plug in has to be an element of W. And what we plug in is we plug in F of row 1 G inverse of V1. So row 1 is a representation on V, so row 1 of G inverse of V1 is just going to be another vector in V1, because they'll send this vector in V1 to another vector of V1. And then F is a map from V1 into V2. Sorry, when I said W earlier here, I meant V2. But anyway, so this F is going to take in this vector in V1 and spit out a vector in V2. And so indeed, row 2 of G is going to be evaluated at some vector in V2, and so it's going to give us a vector in V2. And this works because it's going to be a very similar argument to this one. Yeah, basically you have to so with this argument, what you're going to have to do is you're going to have to use this definition and the G inverse, and it sort of flips itself, and then you have that H inverse G inverse, which becomes GH inverse, and then you work with that. Here you get a similar thing, but you use the fact that, you use the definition of rho star. But anyways, so again, I've left the details out for the same reason. I did have this one figured out, I think, but because I wasn't able to get this one to work, I don't trust the thing that I wrote down for this. But anyways, I'm just going to leave this at here. So this is how we can take representations on vector spaces and sort of put them together to get new representations. And that completes this video.